Hello, everybody, and welcome. This is AGR Breaks It Down, our first podcast here at AGR, where we, as the glass experts, are going to break down some of the concepts in the glass industry for you. I am your host, Dominic Baker. I'm a research engineer here at AGR, and with me today is Dr. Brandon Aldinger, senior scientist. Would you like to introduce yourself?
Hello, it's good to be here. Nice to kick off this new series with you, Dom.
Absolutely. So you brought in a box full of batch material for glass making. And I'm very, very excited to go through this. As a research engineer, I don't get to handle this very much. I do get, chances to put my hands on it. But generally speaking, you're kind of more the expert here. So I'm going to be throwing some questions at you. So let's go ahead and grab one of these guys out here. Let's see what we have here. Soda ash. This might be pretty familiar to most people in the field. Why don't you go ahead and grab this for me? And
Sure. So out of my box of batch materials, these are extra materials that we get for analysis, where we look at the chemical components and the purity of them for the glass industry. So our analytical division, they sent me a bunch of these, and I keep them around for educational purposes. Got here soda ash. It looks white. It looks very powdery. Kind of looks a little bit like sugar, except not as granular. So soda ash, this is a really important part of glass. It's typically in the range of 10 to 13% content. Glass is made of soda lime silica. That's the standard composition that really almost everything that we handle on a day-to-day basis is composed of. You've got your glass containers like bottles, you have your tableware, you have windows, you might have any sort of architectural components, even let's say casserole dishes. Most of those are going to be made out of this soda lime silica glass. A major part of that is the soda part. Soda is just the common English term for sodium, and soda, the ash specifically, is sodium carbonate. So this sodium carbonate here, that gets put into your batch as one of the major ingredients of that soda lime silica. So why is it this sodium carbonate form? Well, that's what's typically mined out of the earth. That's what we are going to use as a raw material. It comes from certain deposits around the world. It tends to be one of the more rare ingredients, or the less common of the three of soda lime silica components of glass. So it tends to be more the one expensive component of the glass. Now, sodium carbonate is kind of interesting because that CO3 carbonate group, that doesn't stay in your glass, because ultimately everything's going to be oxidized in our glass composition. And so that CO3, it gets driven off in the form of CO2, carbon dioxide, which leaves during the initial firing and melting process.
Right. So this has been a long time component of glass making in particular. This dates back all the way, to the Egyptian era, thousands of years ago. Were they also originally using soda ash, or was there kind of a substitute? How did they mine it? Do you have any idea?
Well, soda ash, because it's a little bit harder to find, this was one of the ingredients that they had to do a little improvisation. In the past, there was also something called potash, which is still a chemical name for potassium carbonate. And you can obtain that by lots of burning vegetation, and that'll leave residues that are rich in this potassium carbonate. So that can also be used to make glass, but there are some drawbacks and reasons why we don't do that commercially anymore. This soda ash, though, this is one of the major innovations that allow glass making to take place. You can make glass just out of pure sand. So when lightning hits sand, it will make a glass. It's something called a fulgurite. But it takes crazy high temperatures to melt pure sand, so the pure quartz. There's reasons why you might want to do that. We could talk about that later. But soda ash, that sodium, it actually lowers that melting point. It acts like a flux. And so now we can make glass in ordinary fires and furnaces that people in ancient times, that they could get those temperatures.
So the whole reason why we're adding this to the glass isn't because it's a necessary component for glass itself. It just makes the process that much easier, maybe more energy efficient. Does it do anything in terms of relieving the amount of seeds or anything like that in terms of the glass mix? Or
I don't necessarily know exactly how it would be without pure quartz versus quartz plus soda ash in terms of seeds.
Sure.
But what it's doing is it's making the glass at lower melting point, as I mentioned before. Now it is making it less chemically durable. So we don't just have silicon and oxygen bonds in there. Now we got silicon, oxygen, and some sodiums interspersed, and this particular glass now it could be attacked by water in the environment. So if we just had soda and we just had silica, you can make glass, and that product is called water glass. We use that in different types of metal industries, but that product wouldn't be any good for containers because it's water soluble. Okay. We have to use other things.
And that's why we had that third component, right?
Right, the lime.
The lime. In fact, I believe, do we have lime in here?
We do.
We do. Actually, here, let's talk about this next one here. This is actually a very typical component. Sand, actually. You find that just about anywhere.
So this is sand. It looks almost like any normal playground sand. A little bit more pure and more consistent in size probably than you would find just at the beach. You won't find bits of seashells in this. Sand is, of course, the major component, somewhere upwards of 70% of your typical soda lime silica glass. So you've got to have sand. And in fact, having a nearby source of sand is one of the main qualifications or benefits of trying to locate a glass plant. You want to find a relatively high purity source of sand, and they vary because sand.
So let me real quick. What is a high purity source of sand? What am I looking for in a high quality sand?
Ideally, with sand, we want to have just the SiO2, just the silica. If we have other types of contaminant minerals, because remember, this is coming out of the ground. It's not necessarily like we're getting it off the beach or something. We're mining it from a deposit. There's going to be other minerals that could potentially be in there. And some of those minerals either don't dissolve very well. They're little particles of what we call refractory heavy minerals, and they are going to not dissolve and come out in your glass as defects. You can also have excessive amounts of iron impurities. Iron's a very common contaminant in sand, and that iron will actually cause increased coloration of the glass, typically a greenish color or a kind of a yellowy color, depending on the oxidation state of the iron. So to have more clear glass, we need higher purity levels of sand, and different deposits have different levels of purity and hence different costs.
Absolutely. In fact, I think we have a couple of the samples in here that include iron in the mix.
Right.
So it's not something you want to completely eliminate necessarily, but not great in larger quantities. So we have to purify kind of our quality of sand before it comes in. Is that what you're trying to say?
Not quite. It depends on the product we're making. So if we are making a tableware or we're making a crystal glass, we want to have no iron, as little iron as possible. Or even back in my ballistic days, we had something called low iron glass, which was flat glass meant to have the highest transmittance possible. So they wanted to try to use high purity sand to achieve that. If we're making something like an amber beer bottle, though, that color requires lots of iron. We don't really care that much about the sand source. So you can use a cheaper, higher iron content sand for that product because we are actually going to need to add more iron in there to get certain colors of glass.
Interesting. So I'm actually going to take a quick break about talking these particular compositions, these batch materials, and I want to ask you, because it's a common question we get all the time, if I'm changing the composition of my glass, am I going to get varying degrees of strength in terms of how I can abuse my bottle down the line?
This is a pretty common thing that we're asked a lot if there's a breakage problem. Can I change the composition of glass? Or, hey, I'm getting glass from a different location and their glass seems weaker than my glass. It turns out that the glass properties like fracture toughness and hardness, they don't really change much within a particular compositional range. So for soda lime silica glass, for all intents and purposes, the composition is not going to be the dominant factor of your fracture. That's almost certainly going to be negligible. So the little tiny tweaks that a glass company might make to their glass composition, putting something up 0.5% or 1%, it really isn't going to affect the glass strength. We know that as part of fracture analysis, the surface strength of glass is really what determines how strong it is, and that's related to the handling and what types of defects are present. It's not going to be affected by the composition.
Yeah, and we teach whole schools on this subject, Fracture 1, Fracture 2, and Fracture 3, all available in person. We do this around the world. You can check out our website to see when those would be scheduled, if one would happen to be near you. We also have online seminars, which you guys can also check out. They might have a link down below, so go ahead and check that out. But all great things, to discuss. Let's go right back to some of these materials. Let's see. This one looks like a fun color. Ah, there we go. It's like a pinkish, powdery, almost like a flower. What would you call this?
Yeah, so we got a very Easter pink looking color here, pastel. This is an element, well, compound of an element. It's called erbium oxide.
Erbium oxide, okay.
So erbium is a rare earth element. It's one of those elements that you see at the very bottom of the periodic table, somewhat over my shoulder if you're watching the video. Erbium is pretty neat because it is used actually as a decolorizing agent for glass. When we are making glass, I mentioned the iron impurities that can be present. Well, that iron impurity, that is going to impart either a greenish color or a little bit of a yellowish color, depending on the oxidation state. We don't want that color to be there if we're making so-called flint glass, which is just a synonym for clear glass. If we're making that clear glass, we typically want to try to get rid of as much color as we can, but there's really no way to take that iron out once it's in there. So we play a little bit of a trick on your eyes. Turns out your eyes are really bad at seeing faint shades of gray. So what we're going to do is we're going to add in little bits of other colors to balance out that either greenish color or sometimes a little bit of yellowy color that you can get from iron. So for the case of container glass, we're actually going to add in typically a little bit of cobalt, which makes blue, or a little bit of selenium, which makes pink. Now, those elements are relatively common, or those are relatively inexpensive ingredients. But if we want to make much more higher transparency glass, we're looking at a higher end product, we can use something like erbium. So instead of using an ingredient called selenium to get our pink color, we use erbium, which has a bit of a tighter transmittance. We don't have to add as much, and so we're going to have higher clarity, higher transmittance of that object. So the erbium will give us a pink color, right, and that's going to help balance out any green that's present from that iron impurity.
So you say it's a decolorizing agent. So what we're doing is we're taking kind of the opposite end of the spectrum of light, of the color, right? And we're pulling it towards that side.
Right.
So it's not necessarily we're coloring it to be pink, we're just pulling it away from that green, and we get into that neutral territory of the flint glass that we're trying to achieve.
Yes, we're going to shift our glass to a neutral gray, which is so faint your eye can't see it.
You can't detect.
Your eye could detect a little bit of green when it's there, but now that little bit of grayish color, you aren't going to see that.
Now, would I ever use this to get a pink colored glass? If I added more, would I eventually get
So
there?
you can get pink glasses. Erbium will make a nice pink if we really wanted to, and so in the sense of like art world, if you want to making a jewelry item or a fancy tableware type of item that's intentionally pink, you might select erbium. Now, there are other elements that may be less expensive to do that with, but erbium could be used for intentional coloration. Sometimes it's used to dope as a dopant for lasers, where you can get an emission color that's kind of a pinkish, I believe, pink or red color.
Pink laser. I don't think I've ever seen one of those before.
Well, it'd be mainly used for, I believe, research purposes.
I see. Not commonplace. I'm sure it's a little bit more expensive than what most people are willing to buy as a cheap little laser pointer.
Yes, that's a different type of a laser,
Yeah.
a diode laser.
Awesome. Well, let's go ahead and grab another one of these batch materials out. Let's see here. How about this guy? We got some calamite slag. Now that's got a whole bunch of different colors and particulates in there. So why don't we go ahead and give this one a go?
Okay, so this bottle I'm holding, it's got kind of a beigeish, grayish color. It looks like almost like a dirty sand. It doesn't have a difference in size, really, but it's got different colors of whitish and gray. This is a waste product, believe it or not, from the blast furnaces used to make iron. When you're making iron metal from ore, you got rocks that come out of the ground, and these rocks have iron in them as well as other silicate minerals. You're heating them up in a blast furnace, you're melting them, and the iron is going to get reduced into elemental iron, and now that's going to sink to the bottom of your furnace, and it gets drained out. Now, all the other stuff has to go somewhere, and you end up with this molten mixture of silicates, which is these glassy types of material that floats to the top.
And that's the stuff we wanted. for our glass, right? Our batch material.
Well, initially it wasn't used. It was waste products. So this is why if you go to old iron furnace sites, even around Pennsylvania, here in Western PA, there's a lot. You can find slag, which is just glass. It's artificial man-made glass. Usually is a greenish or black or gray color, and that was a waste product. But they found out that, hey, you know what? This product is actually valuable for making glass because it's got alumina in it. Now, alumina is a very important minor component of glass, typically in the 1 to 3% range for a common soda lime silica glass.
Still important, but
yes,
nothing like sand.
And it helps with the chemical durability. It helps it to resist attack by water and to maintain a nice appearance. It doesn't get fogged up over time with that addition of alumina.
Sure.
So we need to have that alumina in there. And to get that, we can either go to different types of minerals that come out of the ground, or we can use this kind of ready-made product, this waste material from the iron industry. So the name calamite, it's got calcium, aluminum, and then silica in it. So it's a calcium alumina silicate. And those other minerals, calcium and silica, we still need in our glass, but we're really after the alumina when we buy this and use this. So this is an interesting case of one industry's waste product is being used for another industry to help make our glass.
One man's trash is another man's treasure, right?
Right, yep.
Exactly. So that's fascinating. So when we use this, obviously we're going to need to kind of lower maybe a little bit of the silica and the calcium in other areas so we can introduce this calamite slag, right? Because we're introducing all three of them, but we're specifically looking mostly for that alumina. Now, what does this do for us in terms of the glass making process? When we add alumina, what does it do?
Well, adding alumina actually makes glass harder to melt and can raise the amount of energy that you need to make the glass. So this is one of the reasons why, even though more alumina is in some senses better to make the glass more durable and it has certain other properties, typically we aren't going to go too higher because we don't want to increase the amount of energy and decrease the workability of that particular glass.
Right. Awesome. All right. Well, I got one more I want to pull out from this box. So let's go ahead and let's grab this guy. This guy looks fun. Oh, that is a nice deep, almost like a royal purple or a reddish purple to me. Copper oxide. I'll give that one a go.
So we've got a bottle of very finely powdered copper oxide. Copper is an element that we can use as a coloring agent in glass. Typically, we want to get copper in there to make a nice, kind of a light sky blue color. So the Bombay Sapphire gin bottles, that's a bottle that's colored with copper and has a really beautiful kind of light sky blue, robin's egg kind of color to it.
I would not have guessed that looking at that material that was going to give me blue.
That's a really good point. So this copper oxide is this dark reddish purple, kind of a maroon color.
Yeah, that's a good way.
And copper, like other elements, it has a variety of oxidation states. So it can have different numbers of electrons that are missing from its outer shells, and that gives it different color properties. So similar to our selenium, similar to our irons and other elements, we can alter whether that furnace is relatively oxidizing or relatively reducing, and that will give us different color states. So copper typically will give us a nice light blue color when it's in the glass. However, there are other processes where we can use copper along with other elements such as tin that can form complexes that can give us actually a deep red color in our glass too, which maybe is more like what you would associate with something colored by copper. And so those processes, those are more complex than just getting that nice light blue color, but you can use copper to make at least two colors.
Now, from my understanding, there's also a way to kind of thermally treat this to get other colors as well, just using that material. Is that true?
Yeah, so making that reddish color involves also what's called a color striking process, where we are going to reheat that bottle up in a certain temperature profile after it's been made, and that is going to help the formation of those complexes, and we're going to get that color that will appear in our containers.
Interesting. Well, it's fascinating. So this is specifically a colorant, which is different than the decolorizing agent, which was erbium, right?
Right. So you would not normally add copper unless you wanted to have a certain color being produced.
Interesting. And like you said, it's got a large color range. There's a lot we can do with this. Now, obviously, sure this is not a very cheap material to throw into the batch furnace.
Well, yeah, like if you've seen the prices of copper and copper wire pipes and things like that,
Certainly.
copper is a relatively expensive element. It's a noble metal, and so it is not going to be cheap. It's pretty heavy if I feel this, so it is something you only add if you want the nice color.
Absolutely. All right. Well, you know what? I have a bag here. It's gonna be a little bit difficult to see, but this is, from my understanding, glass cullet, right?
That's correct. So I don't have a pretty bottle for this, but what this looks like is kind of if you took a bunch of random glass bottles and you threw it in a blender, and you would come out with little tiny chunks that are slightly bigger than a grain of sand. So here I can see green particles in there, clear particles, amber colored, and even some blue ones in there. This is what we call mixed cullet. So it is cullet from a variety of different containers, just all different colors that have not been sorted, and it's been ground up and is ready to be used in a glass furnace. Cullet is a really valuable raw material for our glassmaking process. It turns out that we are going to get a number of benefits from cullet. So not only are we going to recycle the glass, but we're going to be having some significant energy benefits. So I think it's every 10% or so of cullet we use in the mix, we save a couple percent off of our energy. It takes less energy to melt cullet than it does to melt all these raw ingredients because all the chemical reactions have already happened. So glass can be melted back into any other shape you want, really, if we just provide enough temperature to get to where it can flow again. So we're really not losing anything, and we're going to use this as our raw material to supply some portion of our batch. It can be really high. I mean, in theory, you can fill a whole furnace with cullet and melt it. We don't practically do that, but we can go anywhere in the range of up to 60% on a routine basis. Usually, glass companies are down more in the 40-ish% for a mixed cullet. If we're trying to make flint glass, we may use a little bit less cullet because we want that clear color. We don't want to risk any impurities in there, especially with it's hard to sort out all the color.
Yeah, I was just about to say, I'm sure it's very difficult to sort when everybody's throwing all the same glass containers in the same bin. You got your greens, your blues, your ambers, your flint, everything, and going all in at once.
Well, that's true here in the United States. In Europe, they actually do different colors. So they have different colors of bins in Europe.
Good
so they have
guys over in Europe.
They have a flint. If you go there, you'll see it like a kind of a big recycling stations every block or two, and they have like a hole for flint glass, a hole for amber glass, and a hole for green glass. So there they are able to separate those colors much more efficiently, and so you can get higher purity cullet over there versus here. Now there are ways to sort cullet. There are machines that do this, and they can visually look at the bottles and sensors and things, but it's still not a perfect process because after all, you're dealing with post-consumer waste, and so you're not going to get pure. Now, this is external cullet. This is the stuff that comes from outside of a glass plant. There is also internal cullet, which that's just all the basically unusable containers or broken bottles that a glass plant makes, and that is, of course, pure because that's their own composition. It just might, for whatever reason, not be packable ware, and they will recycle that internally, and so that's high purity.
Awesome. So there's ways around getting some nice purity glass, and one of the nice things about glass as compared to, say, something like plastic is it is what we call endlessly recyclable, right?
That's right.
So yeah, I'm going to take that from you. In fact, we're actually going to get into some LinkedIn posts a little bit later here that will kind of talk about that. But before we do, we actually have an analytical lab in Maumee that does a lot of analytics for this particular stuff. Do you want to go ahead and talk to me about what they do over there?
Sure. I'll hand this to you real quick.
Yeah, sure.
But yeah, our lab in Maumee, Ohio, which is near Toledo, they really will handle analysis of bulk glass. So if you've made glass and you want to know what's in it, their most common technique is something called XRF, X-ray fluorescence, and that gives you pretty good accuracy down to fractions of a percent of the composition of the components in your glass. If you want to know about these raw materials, they can do different types of tests. Some of them are more chemical analytical, like where they have to dissolve things and titrate, and some can be done via the XRF technique to look at the purity of the components. For instance, like if you get cullet, you want to know like what is the mix of the compositions, because you're basically taking an average composition of all the plants that made those glass bottles, or the calamite slag. You would want to monitor that composition because the rocks that go into that iron blast furnace, they're going to vary because it comes from a mined quarry. So
Based on your geological location or wherever you're mining that.
And a big one is sand. Monitoring the iron levels in your sand, you want to know that because typically you're very concerned about the color. For certain industries, need to know like that their iron's below a certain level so that they can be guaranteed of having meeting their color spec for flint glass. So there's a lot of different chemical things that can be monitored as well for this. There's many other types of analytical tests for glass components, such as what's called electroprecipitator dust, which is a material that's reclaimed from the furnace, that's from the exhaust. That's something they can analyze as well. But really, just doing these specialized tests for glass products, it's not as easy as you might think because a lot of labware, it's made of ceramics. And ceramics ultimately usually are some kind of a silicate material. They're going to have the same components in those labware that's made with glass. It's in the glass. So you can't use them to analyze your glass. So what are you going to do? It turns out you have to use very special techniques and special containers, typically made of platinum, to analyze glass-making components. Not many labs are set up to do that.
Not many. So almost peerless, I guess, in terms of an analytical lab, in terms of glass in particular.
Well, we've been doing it a long time, so we're very well known in the industry, and we have a lot of trust built up, and just again, a lot of these special tools that are needed to be able to analyze these components.
Yeah, absolutely. So if any of you have issues with chemical compositions that you would like to tackle, obviously our people over at Mommy for their analytical lab can help you out. So reach out, see what they can do for you. They do tons of analytical tests, as Brandon has put forward. And on top of that, I would like to just take the time real quickly. We have way more glass compositional items to go over, but in interest of time, we're not going to go over those today. If you are interested in learning more about these things, go ahead and comment. Let us know. Do you want us to talk about more glass compositional items, some of the batch materials? I'd love to hear from you guys. So talking about hearing from people, I actually have printed out here, because I do like paper, a couple of LinkedIn posts that I would love to discuss with you, Brandon, kind of on this topic. So the first one I have here is actually from Sabre Glass. This was quite some time ago, but they said components matter. While silica, soda ash, and limestone, we did talk about quite a few of those today, make up about 95% of the composition of glass, the remaining 5% of materials are no less critical. So they're saying these materials, that 5%, affect the mechanical, chemical, and optical properties of glass by influencing its brilliance, radiance, and color distortion. So that's quite interesting. The combination of these characteristics is what enables Sabre Glass's extra white glass to magnify our customers' products. Now, we know them to be quite high quality when it comes to some of their glass colors and the quality of their glass overall. But what struck me here was they said the 5% there, those materials affect the mechanical, chemical, and optical properties of the glass. Do you want to talk a little bit about that? Like what really goes in? We have some of the colorizing agents. Do they affect, if I'm trying to color a bottle, am I going to get a different strength? We talked about it a little bit, but I kind of want to hear your opinion here.
Well, typically, the colorant won't affect the strength. I think they might be referring to things like alumina, which do have an effect on some of these properties. But typically, at least, again, on the standard soda lime silica composition, we may not see too much effect on mechanical properties, like hardness. If we really start getting into a full aluminosilicate glass like is used for your cell phone screen, now we're talking a much different composition, and you are affecting things such as fracture and hardness and other properties mechanically. Certainly the brilliance, and I think what else did they mention?
Brilliance, radiance, and color distortion.
Okay, I'm not sure what they mean by radiance, but certainly color is important, and the brilliance is another factor. You can affect, by adding smaller amounts of heavier elements, the refractive index of the glass, and this is going to be something typically referred to as kind of the brilliance of it. So we're going to be able to now have glass that looks a little bit more shiny, that refracts the light a bit. You get a little bit more of maybe a prism type of effect. This can sometimes be done by adding elements such as barium or heavier elements instead of using all of the calcium. You can now add some potassium, which is even a little heavier. And now we're going to, typically heavier elements are going to give you a higher index of refraction, and you can end up with have a little more dispersion property, which gives you different refractive indices at different wavelengths. And now we can get a little bit more of a prismatic effect, a little bit. It just looks more, I guess, closer to the chandelier end of the spectrum rather than just a plain old clear bottle.
Right. And for those marketing people, I mean, that 5% becomes critical at that point, right? If you're trying to market yourself as a particular brand, maybe it's the absolutely clearest flint that you can find. Perhaps it's like your Coca-Cola green. You're very specific about the color. Those 5% extra chemicals that we throw in there are critical, as they're saying here. Which
right, there's certainly a lot of marketing play here. What kind of brand image does this company want? Really, when we get into things like brilliance, we're typically talking like the clear glass. We're trying to get our glass to look really sparkly, really high end. So high-end liquor bottles, high-end vodka, things that are sold in clear containers. That's really where this is going to come into play the most. Then the unusual colors, that can be used to grab the eye of somebody who's trying to shop for something. They see something really different, and they might select that product versus another product.
Is there a particular color of glass that you hold a special interest in?
Well, yes, but it's not found typically in anything you would buy in a container glass. I really like something called Vaseline glass.
Vaseline glass.
And Vaseline glass is colored with uranium.
Oh boy.
So uranium, as you know, it's very, very slightly radioactive in the glass. So in the glass, it's locked in the composition. So don't worry, folks. I'm not gonna die of radiation poisoning. The uranium is in the oxide form, and it's again, it's in the glass structure. It's not coming out. But it provides this yellow-green color, which is very vibrant because it actually fluoresces under ultraviolet light. So
no kidding.
In sunlight, you have a little bit of ultraviolet light present. That's why you wear sunscreen. And that UV light is actually fluorescing in daylight. So in addition to the yellow color, there's also the green fluorescence added to it. So it has this very vibrant yellowy green color.
Oh, that's
and
super cool.
It was much more common back in the early 1900s to make different types of tableware or servingware out of this.
You know what? I've seen a couple of antique stores that hold this yellowish, greenish type of glass. You're saying that likely had uranium in it.
Yes, it does have a little bit of uranium. Now, back in the day, there were some kinds of weird marketing things involved with it where they thought it would do something magical to the water that was in there. But mostly it was just for decoration because it was a pretty neat color. And so today it's much harder to find. It's too expensive to use in glass bottles. But there are still some art glass companies that make usually pressed glass items or molded glass items out of uranium. But it's very common still on things, eBay or any antique place that you can find it. So I do have a small collection of uranium glass, or Vaseline glass as it's called.
Awesome. Maybe one of these days we'll post one of those on LinkedIn, and you guys will be able to see, if you follow us on LinkedIn, some of that uranium glass that you have a special interest in. Okay, I got one more post that I'd like to talk about. This comes from Alex Dubrow, and he is talking about kind of a sustainability standpoint, or what he likes to call the circular economy. Now, I'm not going to read the whole post here because it is quite lengthy, but I do have a couple highlights here. He says, you recycle a plastic bottle, you get a new one. You recycle an aluminum can, you get a new one. That sounds about right, right? The answer is a little bit more nuanced than that. So paper can actually be recycled about 5 to 7 times. Plastic, only 2 to 3. Now, metals, such as aluminum cans and glass, those in particular, can be recycled infinitely. So why the stark difference? Now, he says here, according to the professor of environmental history, Finn Jorgensen, as the paper is broken down or recycled, the fibers get shorter and less flexible. That is more or less true for plastic as well, as its chemical composition changes during reprocessing, thereby decreasing quality. Metals and glass, on the other hand, can be melted down and remolded into the same high-quality product that was recycled. So that's fascinating, right? What allows glass to be endlessly recyclable, unlike, say, paper or plastic?
Okay, so there's a lot of things, but the real main factor is that if we ignore all the other stuff, glass is made up of primarily SiO2 and all sorts of oxides of different elements. When we are melting glass back into whatever form we want, making it molten and then into another shape. It's staying in that compound, in that form, in the oxide form. So we're not changing its chemical structure, we're just changing its physical state. Same thing with like aluminum cans. That's the element aluminum. We're not changing its actual chemical structure, we're just changing its physical state. We're melting it and then we're making it into something again. Whereas things like plastic, we're actually changing how long those chains of carbon atoms are, and there's no way to get rid of impurities. So with glass, let's say we have a bottle, it has labels on it, it has somebody's spit in it, it's got whatever gunk left over of the product.
Sure, gum stuck to the bottom of the
That
packet
all
or
is going to get ground up, and it goes into a furnace, which is going to just incinerate all that stuff, and it just turns into CO2 because that's all organic matter. So all of our contaminants, typically just the organic stuff that it's going to pick up, that basically goes up a smokestack, or it somehow gets reclaimed, but it's not going to end up in our final glass because it's made up of these oxides. So this means that glass can be recycled again and again and reused. Glass also doesn't really have a distinct melting point, which means that it can be it's a continuous curve from a solid up into we get into a liquid state and then back again. So this is also part of the reason why we can melt and reform. We don't have to necessarily worry about any sort of loss of the glass during those processes.
And we did talk a little bit about that glass cullet and how you said sometimes it reduces the energy that goes into producing bottles if we have that glass cullet. So in terms of sustainability, in terms of recyclability, glass has kind of got a head start on some of the other materials that we have, at least in terms of packaging, right?
From an energy standpoint, yes, you also have that savings. We don't have to redo that reaction, that chemical reaction. Of course, you have the raw material savings because we don't have to mine more stuff out of the ground, which you have with any sort of recycling. It's the justification. But you do have that energy benefit. The logistics, that's really the kicker, especially of trying to get that post-consumer waste back into the hands of a glass plant, especially in a relatively large country like the United States, where glass plants are very scattered far apart. Communities are more dispersed. It's hard to get those collection streams to work. But in countries that are more compact, like in Europe, they have that process much more streamlined. They're also used to recycling in that different way where waste is separated, whereas in America, we put all of our recyclables into one bin. And so that's the multi-stream versus single stream. That also is a logistical hurdle to recycling. But from a sheer just chemical perspective, there's a lot of benefits to recycling glass, and it could theoretically be done in 100%.
Well, that is awesome. One last point before we go. Alex continues on and mentions a survey conducted by Consumer Action. Now, quote, they found that 58% of American respondents believed plastic materials are endlessly recyclable. So we're kind of stuck in this, at least the majority of us Americans believe that, plastic's endlessly recyclable. If we recycle our plastic straws, our plastic containers will be okay. We're not going to hurt the environment or anything. Do you believe there's a way that we could possibly change that sentiment? Is there any opinions they have on that? Because that's kind of worrisome a little bit.
Well, the glass industry has tried to impress upon people how environmentally friendly glass potentially can be. There are some other benefits. So in addition to glass being recyclable, it doesn't really pollute the ocean because if somebody drops a glass bottle in the ocean, it sinks. It's basically a rock. It does nothing. It doesn't hurt the fish or anything.
It's naturally occurring.
A turtle's not going to eat it or anything like that. Whereas plastic floats around and you get these big zones of garbage in the ocean. So there are some other benefits to glass. And there also is a perception that glass is healthier in the sense that you don't have leachable compounds, organic compounds coming into the product.
That uranium sinking into your food when you eat it with
nobody really eats out of the uranium glass. But you don't have... you don't have any leachable like the BPA thing and this, the plastic liners and all that.
The microplastics that have kind of been trending.
So really right now we are in a phase where plastic is trying to become more recyclable, more reusable, and glass
let's hope that it gets there.
And glass is already sustainable in the sense of its material, but it's trying to become more energy efficient in the production. So that is one of the challenges. And it really does come down to different types of legislation and then consumer perception of value and of product quality. But people do think that there is this perception in the United States that when you put a plastic in the recycle bin, that it comes back to you as a new plastic bottle. But that also is not always true.
Okay. Well, thank you, Brandon. For all of you back who are listening, thank you so much for tuning in. If you have any opinions on the sustainability and recyclability of glass, I'd love to hear it. Let's continue on to the discussion. Maybe you might be part of a larger company. Maybe you guys have plans. Now, obviously, we don't want you disclosing things that are NDAs or anything like that. But if you have new methods of energy savings or areas of interest in terms of the sustainability in glass, it's kind of a big thing going on right now. Would love to hear from you guys. But with that, pretty much set to go. So go ahead, follow us on YouTube, follow us on LinkedIn. We're going to be doing more content like this. Let us know what you thought, and we'll catch you later. This is Dominic Baker and
Brandon, thanks for listening.